The sound check. Can you hear me clear?
Yes.
Yes, your audio
Perfect.
feed is coming through well.
Thank you. All right, let's begin. I'm going to share screen. You see just the slide right now?
Yes, weather and astronomy.
Let's begin. Thanks for having me, by the way. It's been a while. So today the presentation is going to be explicitly about weather and astronomy. Something that we all can relate to, and something that we can all of us are dependent on, whether we do astronomy, sailing with our boats, or going out on vacations or travel, etc. Weather is always the one that determines the outcome of our fun, pleasure, mood, everything. So now let's begin. So I'm working at AWI, which stands for All Weather Incorporated, which recently was bought by ADB Safegate, which is a multinational company. All Weather is the main office is here in Sacramento. It has offices in Colorado and Texas, and the business is about creating weather equipment and other types of sensors in relationship to airports and aviation, aerospace business. So there I'm standing on some servers that are simulators. You can see on the top are some clock servers that we have. It's very important with time accuracy in those servers. In the middle is how we normally every day we talk about algorithms, how we communicate between the sensors. That's a typical day for a software engineer. On the left-hand side, we have a snapshot of a weather system as a air traffic controller sees it. Below is my desk with my code as I see it, and how I, crank through math sometimes when we do weather algorithms, and of course I share the same passion like all of you, which is astronomy. So that's my telescope that I recently upgraded to be more accurate on its guiding. Now, aviation industry is super sensitive. It's very regulated, enormously regulated. Every little bit of it has laws, regulations, and many local airport rules to accommodate the needs of many traveling passengers, and also the safety in all people that partake on this service of transportation. Air traffic controllers have a very difficult job to make sure that this traffic is flowing, making sure that all the data present to the pilots while traveling is correct. Pilots are receiving data for altimeter setting, which comes from our weather algorithms that determine the height for landing to the airport. So all that stuff is paramount to work. There's backup systems whenever power goes down. There's other safety systems that kick in. There's other airports that take nearby airports that come take control in case something happens with the existing airport. There are many parameters there that back up air traffic control in case something unexpected happens. Now, in my line of business here, we design hardware and write the software for our own hardware. They're designed and manufactured. Some pieces are manufactured across the states, others here in Sacramento. We assemble everything here in Sacramento, in Natomas. And some of you might have realized the weird antennas and boxes and some kind of weird equipment by the side of the runways. We have actually one of the ASO systems that is mentioned here in this picture is actually located also in the Blue Canyon Airport. You might have seen it. It's like yellow in color, some wind speed meters and so forth. All those sensors are actually, even those that you guys have by the Blue Canyon Airport are manufactured going through us, and we actually work together with another Finnish company called Vaisala. So those sensors, particularly in Blue Canyon, are from Vaisala, but we are the ones that install them and make sure they're operational and so forth. What's the difference between an AWOS and an ASO system? The one we have at Blue Canyon is an ASO system, which is really, really remarkable because it provides much more data. An AWOS system typically provides us with the weather data when it comes to clouds, obscuration, it's other sky conditions, the visibility, which is very paramount for astronomy, temperature, dew point, and other two important factors for astronomy. The altimeter setting, which is very important for pilots, determine the, especially for landing, how far it is down to the ground, so they don't smash down with their airplanes. The spin direction is also very important for aviation, but also for astronomers. We're going to deal with details for each of those factors, and gas and the direction of the gas. Now, additionally, the ASOS has precipitation types. The one in Blue Canyon is reporting actually if the precipitation type is of rain, snow, or something in between, right? And then, of course, obstruction of visibility. It's determined whether or not it's based on fog or haze or other things. We will look into that. Now, those weather reporting systems are reporting two different messages. Primarily METAR is the most commonly used, which stands for Meteorological Terminal Air Report. It provides wind direction, wind speed, the air temperature, barometric pressure, and cloud cover, which is the most basic things you can have for an unmanned airport. But additionally, TAF is completing that list by accumulation of data, and through algorithmic analysis, it provides some kind of forecasting over those gradual changes, whether they were gradual or quick, like a gas, a quick change, a gradual change in temperature is something else. So all those parameters are what we call in the industry as products, are taken care of in different ways. Now, when I started working at ADB SafeGate, or AWI as it was called primarily in the beginning, they brought me a sensor from a runway, which is a light sensor that's installed under the asphalt of the runway, and just let the cap, so to speak, here on the top to be above the ground, so to speak. And this is the middle line, during nighttime when the planes are landing. That's what they're seeing during specific angle, so to speak. And that angle is also very, very specific as to when they come bright or not. It has different colors. Now they gave me a hammer and challenged me to bang at this thing as hard as I could, and it didn't feel natural, of course. But this equipment here supposedly can withstand an entire aircraft, like a 777, the biggest Boeing in the world, to land on top of these lights without anything happens. So a hammer won't do anything. But it was against my instincts to hit that thing. Other types of lights are those that determine whether or not you reach the end or the beginning of the runway. And then finally, everything is interconnected to what we call for data control processing units. Those are located in the middle of the runway or at the end or beginning. Some airports have them at different locations. I will show you where those are located normally, most commonly located. So you guys, next time you travel, you can see those. Now those units are gathering the data from all sensors and parse it through firmware, software, and then I'll show you how that data looks like, and then finally ends up on the air traffic control screens in an orderly manner. Now, there are many different types of well, not many, but there are some different types of sensors. In the first picture here, we see a ceilometer, and ceilometer is a responsible equipment that determines the height and the amount of cloud right above it. So it shoots a laser from one of the mirrors inside straight up, and then calculates as the light bounces back how high up the cloud is located and what type of cloud it is, and how many layers it penetrates. It can do that very accurately. There's some cloud height indicators or ceilometers that I actually use only one laser that's both sending and receiving, but in our case, in our model is having two of those for backup purposes, I suppose. The next one is a rain bucket, which is a bucket that gets installed on those tipping buckets on the right side. We see inside the bucket how it looks like. So the rain drops and then it tilts and empties its water. It gets measured and then tilts back and measures in the other bucket. And those are the so-called tipping bucket mechanism for measuring rain and type of rain and so forth, like we said before in the ASO system. Wind sensors, you guys have seen probably in the past that we use those propeller-like wind sensors that rotate, and those are the old mechanical. And as demands in the aviation start increasing, those mechanical parts, the more rotating parts, the more moving parts you have in a hardware, the more maintenance, they're going to break, they're going to have to be, maintained very often. So the less moving parts you have, the less maintenance you need for those. So now we use ultrasonic sound to measure wind speed, which is kind of remarkable, technology. Temperature sensors is just like a mini microphone, a small microphone that goes inside, and it gets protected by a solar radiation shield, so we don't get fluctuation and false registrations of temperature as, from morning to night as the temperature climbs and decreases. Now, another type of sensor is the visibility sensor. And that's, we have a light that shoots between those senders and receivers, and whatever particles we have in between are getting registered. And the thickness and amount of particles will determine the visibility of air. It's a typical runway. As you can see here on the left-hand side, we have a weather station. Normally, they are either at the beginning of the runway. Other times, they're located in the middle of the runway or at the end on the other side. In this case, we have it in the beginning, the end. And because this configuration of runways is like a big V, they put them, because there are FAA rules in the United States and international, we have ICAO, so-called standards that are regulated by the United Nations and the international aviation industry. Those are strategically placed so airports don't have to pay large amounts of sensors. So they strategically place them by the accordance to those rules in strategic positions to have us the minimum allowed sensors in the right location to measure, wind gas and so forth, to provide the accuracy of data that pilots need to operate the aircrafts. Now, another detail in this picture is that runways have numbers, and what those numbers are is that based on magnetic north, we count when they pave a new runway, they give them designations, whether they're left, right. So L stands for left and right is on the other side, R. 21, you put the zeros, is 210 degrees from magnetic north. And if you do 210 minus 180 degrees, you're going to get the number on the other side of the runway. So those numbers are specifically for identifying, the bearing of the runway, so to speak. Now let's talk a little bit about our runway. Here you see 330 degrees minus 180 is 150 degrees. So those numbers are accurate here. And then our little ASO station here close to our observatory is right here. And you probably, when you drive down the car here, you probably notice it across the bushes and trees here. You can see some parts of it. But yeah, you can stop the car at one point and just walk by and come close, and you will identify those type of sensors we just spoke. They have a fence that protects those because it's unmanned airport, so nobody else protects them. There's no security here except cameras in a couple of buildings here. Otherwise, they're practically it's an unmanned airport. And then you will be asking, how do the pilots control the light during nighttime if they happen to want to land during or take off during nighttime? Is they radio in a special frequency here through the radio in, and the lights turn on. So practically, if you have a walkie-talkie and chime into that frequency and click a couple of times, the lights are going to turn on. But that's something pilots know about. This is information. I'll show you where you get all this information. It's publicly available from FAA websites. We'll get into details about what this information provides. But for us astronomers, it can be useful for knowing the altitude of our observation site. So even if you're not in Blue Canyon, you can always acquire this data by going to this map I will show you later, to acquire this data of local weather and what your local elevation is with great accuracy, including GPS coordinates and other type of information that we will go into soon. Now, there are two types of air traffic controllers. The ones are in the tower. They direct traffic on the tarmac, when parking and non-parking aircrafts, loading and unloading passengers or cargo. And then when the planes are positioned to take off or land, that's when the handover goes from the tower to lower levels in the airport in some other room. In this case, what you see on this screen, it's a screenshot of the same software, but is meant for air traffic controllers that work not in the tower, but are focusing on the weather for all runways. So here you have all kinds of runways data shown in parallel. And then at the end, you have the compilation of all data from all runways displaying here in a so-called MET report. We will talk about that soon. Now, this is the air traffic control in the tower picture. They see the runway they want to see. They bring it up. It's the same runway. It's just, in two different directions. So runway 11 and runway 29. And the data that they have, especially for each runway side, and then data. Remember, I told you some stations are shared. Well, this data is shared among those 2 points.
Niklas, we have a question here from Kevin.
Yes.
Is there a way for the average person to connect to the Blue Canyon weather station to get this data?
Absolutely. I'll give you all the information. You guys can read that. Absolutely. And it's live, by the way. It's live data, and that's exciting. Because at any point of time, you can see what the weather is, how much snow we have, that sort of thing.
Okay, thank you.
Yeah, of course. So the weather is so important that now latest news here in the aviation industries, we get the shockwaves sometimes because we really monitor closely news for us when it comes to what happens to equipment, how does it work out in reality and so forth. And there was a shocker here on the 13th of July, not so many days ago, actually, not 2 days ago. And there was actually an Airbus 320 that was about to land, and unfortunately, the air traffic control gave them the wrong altimeter setting. The pilot put it in. It was very bad visibility, but those aircrafts are meant to land on bad weather, anyways. But the altimeter setting is absolutely paramount, a number correct setting for the altimeter of the aircraft. So when he started approaching the aircraft, I'll give you also the article for you guys to read. The pilot realized, the captain realized that it was the wrong altimeter setting, and they just avoided crash by just a few feet. The altimeter was set much higher, much lower than the actual runway altitude was, and so that the plane was on its way to crash down, so really, really serious incident, and it's still under investigation right now in France. This happened in France, in Paris, Charles de Gaulle Airport. Now, what we will bring up here is weather patterns and effects, air and atmospheric conditions, which is, I think, very interesting for all of us who do astronomy. Winds and gas, and what does that do to visibility? Clouds, and how those are affected by temperature. The dew, which affects our equipment, and what remedies and planning we can do to prevent certain elements from attacking us as astronomers, with help from aviation instrumentation, and where we can find these forecasting tools and sources. I will provide them at the end. Now, the types of incoming data from the sensors are the following: is temperature, either in Celsius, Fahrenheit. Some sensors are made for Celsius, others for Fahrenheit. The software is the one that converts from one unit to another at the end of the day, so you can actually switch on and off which kind of unit you want to use. The wind is using SI standard, so it's normally meters per second. The direction is in degrees, of course. I wrote that wrong. It's just the speed, that's meters per second. Direction is, of course, degrees. Precipitation is millimeters, which is an accuracy kind of choice to use millimeters. Solar radiation, which is watts per square meter. And that helps the airports to adjust the intensity of lights during nighttime. That's why it's important with solar radiation. Obscuration, which is measured in OKTA, which is how much part of the sky is covered. That's also essential information for us astronomers. The visibility, which can be stated in miles or nautical miles or kilometers, because it's huge distances. The humidity in percentage, barometric pressure in inches of mercury, lightning, if there's risk for lightning, that information is provided by this equipment. Additionally, what is processed from those type of parameters or input from the sensors, we can produce dew point data, wet bulb temperature, which is how much moisture we lose during hot days, gusts, sudden winds, solar radiation can provide us the intensity of sun, present weather, and present weather is more detailed about barometric pressure and that sort of thing. Visibility, how far we can see. I mentioned that twice, didn't I? Yes. Ambient light, which is the darkness, and that can also be of interest to us astronomers. The cloud-based, transparency, and seeing. So I put in yellow the ones that are of most highest importance for us astronomers. So let's speak a little bit about you, which is an enemy for whether you have a mirror telescope or a lens telescope. It's attacking both kinds of astronomers, visual and astrophotographers. And there's some countermeasures, measurements to do that. But let's dive into what is dew first of all. It's first and foremost is the amount of water you have in the air, and when it's in gaseous forms, and that depends on the temperature. It can change forms into frost, fog, precipitation. It can start, raining, can create mist, fog, or freeze equipment. As soon as the below freezing point water droplets land on a metallic surface, they just freeze and create this solid frozen surface. Now, all that is direct related to the air temperature, and there's certain things that we can actually measure ourselves to find those things. Now, it's direct relation between a higher temperature means higher amounts of water, right, in the air. But water gets transferred, so you can have it can be very local. So you can have something down the valley, Sacramento Valley, typical hotter temperature down there. The water raises and moves up over to the Blue Canyon area, so that happens too. Now, how we calculate is that we divide the amount of water per volume of air. So there's different units. So this is very vague description, but that's how we do it. And then we have another unit called the relative humidity, which is the ratio between this absolute humidity that we talked about and the maximum humidity that can be carried by the air at a given temperature. Now, the dew point that we are interested of is the definition is that the temperature given at a given volume of air, let's say cubic meter, under a certain atmospheric pressure is saturated or not, creates a vapor. That's what it is about. And we've seen, some of us have seen the effects, especially astrophotographers before, because they get it, you know, on the still pictures. Whenever we have long exposures, we see that directly on our lenses, on our pictures, and visual astronomers see that, you know, when they use Schmidt-Cassegrain telescopes and they use the frontal lens there on the front side of the telescope gets covered by dew. And there's some counter or some remedies to that. And the most simplest one is of course, we try to increase the temperature based on the ambient temperature. So what we can do is that we can either use those heat belts around on the frontal part of the telescope, close to the front part of the telescope. Other things, it's combination. It can be used in combination to use help me out here, Raj. It's a dew extension, right? Dew mask. What do you call it?
Dew shield.
Dew shield. Thank you, sir. And of course, you know, I thought this picture here on the end was funny because, you know, some people like to do home inventions. So somebody's blowing with a fan here straight to his camera. But yeah, there are different remedies. The cheapest one is the dew shield. Of course, comes number one, is the cheapest. This one is a good investment. There is some more sophisticated equipment, like Primalus Lab is using some kind of automatic software that has here measures the ambient temperature and calculates through a built-in algorithm how much power should be given to those heating pads, heating belts here, so it adjusts it. Otherwise, you have manual adjustment controllers here that people can set. Yeah, so that's primarily how we shield ourselves from dew building up on our lenses. Clouds are, of course, our worst enemy, and we need to, you know, keep our enemy close to know it, understand it, and why we shouldn't observe in certain occasions when we see a few clouds, but suddenly we go out, set up our equipment, and suddenly the whole sky is covered. So we need to understand a little bit the weather. Of course, we can rely on forecasting, but sometimes forecasting is, you know, local forecasting is not that accurate as it is for, you know, for state forecasting, you know. So weather can deviate enormously between, let's say, the Bay Area and us here in the Valley, or even up in the mountain can deviate with us down here in Valley and the Blue Canyon observation area. So to get accuracy in weather, we need to understand it better a little bit ourselves and not just complain to meteorologists that, you know, report bigger areas. Now, the clouds are divided by altitude. So on the top level, we have the cirro clouds, which is can be found between 7,000 and 20,000 feet. That they fluctuate between those heights. Then we come in the second medium category, the mid-level clouds, which is 6,500 to 20,000 feet. And finally, strato and cumulus. Those two categories are the low-level clouds that move fast and are, you know, the fluffy clouds that we see above our houses. Now, there are certain amounts of cloudiness or obscurity that we report in different units. In aviation, they use sometimes a clear, diffuse, scattered, broken, overcast, and obscured, and that goes in line with what we get from TV news. You know, oh, it's broken, or we have an overcast or obscured. You have heard those terms. But in actuality, we have much more finer scale here, which is, we take the 1/8 of a circle. If you look straight up in the sky and 360 degrees around you, and then you start cutting off the sky into 1/8, depending on how much sky is covered, you get the octas, are called. Octas comes from the Greek word 8, octo. And 0 means clear sky, 9 completely obscured, and then everything in between here. Now, here I put a picture of a ceilometer, which shoots up the laser and penetrates the cloud, like I explained before. It comes back, and whatever diffracts back from the clouds, droplets, gets measured, and we know the thickness of the cloud and the altitude of the cloud. And we have this altitude curve coming back that we analyze in our algorithms. 0 octa, like I said, is completely clear sky, blue, nice sky. 1 to 2 octas are some sporadic spread out clouds. We simplify as few. The 3 to 4 octa are scattered moving clouds scattered around the sky. And 5, 7, the scarceness of these clouds is called broken. It's much more dense. And suddenly, you find position yourself you can't observe at this point. And then overcast, 7, 8 octas and 9 octas, it's completely impossible to see anything unless you have a radio telescope, of course. Now, if you go into details why all this happens, now in cirrus clouds, those are very high altitude clouds, and they reach up to the levels where we have jet streams of air. Those clouds are not liquid, but there are ice crystals like snow. And because of their lightness, they remain a very long time and they almost appear still to us from the ground, like they're not moving. They're so-called persistent clouds. And the cause of these clouds is low temperature in the troposphere, freezing the water up there, and the moisture in the water. Everything freezes to snowflakes and they just float around. The identification pattern on those is just long white streaks, as I wrote here, and feather-like formations. Next category is this cirrostratus clouds, also in the same altitude category. It's the high altitude clouds, also ice crystals. And this is caused by thickened layers of cirrus clouds that stuck to each other, like in several layers. In the identification of those, it's widespread. They cover enormous, vast amounts of sky, and the white grayish veil-like, that's how they describe them. And they get different nice colors as the sunset or sunrise comes. You get this orange, red, beautiful sunsets, so called, as they spread the light around. Yeah, also very persistent clouds. You don't see them moving very fast. So those, whenever you see those, it's like kind of forget for doing astrophotography. You might be able to do some visual there, but yeah, it's not the optimal for any astrophotographer at this case. Next cloud is the CIRROCUMULUS clouds, and those can be moving. They start moving a little bit faster than the predecessors, and also the same altitude in the same category again. Those are much thicker lamps, so they're having some thickness into them. They're not just flat. Also cover vast amounts of sky, and they're very, very persistent. Even though they travel, they keep coming. The ALTOSTRATUS clouds are the mid-layer clouds. We're leaving now the high category of altitude, and we go into the middle. And now we lower the altitude between 6,500, 10,000 feet. Now the water in this case becomes liquid, and depends on the scarcity or density of these droplets. They can cause occasionally some sprinkles, but not any heavy water or precipitation. Now it's cousin ALTOCUMULUS clouds. They provide a little bit more precipitation. Those are the fluffy round formation of clouds, look like islands, And because the room between them starts getting smaller, they tend over time to start gathering and cause a much bigger obscuration than they originally. And that leads us to the next category, which is the stratocumulus. Here's they start coagulating together, and they form the stratocumulus formations. And this is like a hybrid of the previous two categories, strato and cumulus clamped together. This can cause medium precipitation depending on the temperature and wind speed and pressure, of course. That forces the clouds to coagulate faster. Normally, those clouds have enormous, vast amounts of water. So agricultural people welcome them. And of course, we have NIMBOSTRATUS, which is what we call, normally referred to as bad weather. Those are, the typical frontal system that we, 100%, it's going to become rain here with larger amounts of water. And you can see that a little bit in the darkness of the clouds because they obscure the sun so much that, light does not pass, and you get this watery look on them, like a dark blue, gray kind of look. Finally, something that's not caused by the nature, but it's caused by humans, is the CIRRUS AVIATICUS, or CONTRAILS in everyday language. Those clouds are, wherever there are airplanes passing by. Here's one on the picture going up. Those, unfortunately, are persistent clouds and normally deteriorate the quality of our photography because during nighttime we can't see them. And they're, unfortunately, they are there. Like, even if we can't see them, we can find them visually. They're still there when an aircraft is passing by. So unfortunately, those are a little bit sneaky clouds, so to speak. And unfortunately, the air traffic is increasing for every decade. And yeah, even though I work in the business and I welcome that because it gives me work, it's unfortunately, as a photographer, I'm not very happy about this. Let's speak a little bit about air quality and what does that mean to us here, in the astronomy club. The air quality is divided by transparency and seeing. Transparency is when, it can be caused by different elements. One is light pollution that we try to run away from. That's why Blue Canyon is a very, very excellent site for observation. Away from large city lights and in high altitude and surrounded by thick forest. So that's really great for us to go there and observe. So light pollution is one that we can avoid, actually. The next one is, depending on the season or the winds, you can get all kinds of things like particles. It can be pollen, it can be dust particles, and there's plenty of them around us, especially out in the country area. And that's something we need to watch out for. Even we can't observe, it can actually obscure and worsen the quality of photography that we do. And of course, here in California is something else we fight for, is the fire seasons and smoke that can completely eradicate our observation possibilities. And it's one of our worst enemies in all kinds of ways, not only for astrophotography, but also the nature and all it brings, the devastation it brings. Unfortunately, those elements are against us. We can't do so much about that, except the light pollution can be, avoided by moving ourselves geographically away from it. Other than that, pollen and forest fires, it's nothing we can do. It's unfortunately unfortunate events that cause that. Now, the categorization of transparency is primarily in five ranking scale here. It's poor, below average, average, above average, and transparent. And it's I'll give you sources to look into how to determine transparency later on. Another problem we have, of course, is seeing. It's this typical twinkling in the night sky we see on the moon. It's like a watery kind of curtain comes if we've watched the moon craters move. It's this fluctuation of atmospheric conditions, this distortion, and the twinkling in the stars. That has to do with hot and cold air masses moving together, causing this distortion. Because, as a matter of fact, the air is constantly fluid, so we can't do that. The remedy is, of course, longer exposures, using filtering algorithms in our post-processing. But for visual astronomers, unfortunately, they have to wait and, focus their eyes and, over time, get some occasional clear picture through to see their object. Photographers can work around this, again, by exposuring longer periods of time and retrying, gathering more light. For professional astronomers, they remedy that by doing the adaptive optics, as you well know. There's some adaptive optics, I believe, for amateur astronomers. I don't know exactly how that works. I haven't investigated that really, but there's adaptive optics for amateur astronomers as well. Now, the categorization of that is also a 5-scale grade here, from bad to excellent: bad, poor, average, good, and excellent. Just like the cloud obscurity, we have a very simplified way to categorize the severity of this phenomenon. And here are some sources that I will be giving out. So I'm going to export this presentation to PDF and pass it on to Kevin and Raj, and they can distribute it further to you guys. What I want to show you now is a little bit outside the presentation, some stuff. Excuse me. I believe I turned off my... my Chrome. Oh yeah, somebody was talking about the sunspots in the sun, and here we have from spaceweather.com, we have some really nice sunspots. So good luck tomorrow. Hope everything goes well for you guys.
Is that a live view, Niklas?
The space weather, let me see, they actually mention it's actually daily. It's a daily, once every 24 hours. There must be sources where they do that more often for us. Let's see. Now this is a this is a sectional chart, as we call it, and it's what you can see here is all those available weather stations around. So what you do is it's one of the links I gave you. You can open up. What you can actually do is search the airport code that we have on Blue Canyon, which is KBLU for Blue Canyon. And that will bring up the AirNav website here. You can open it up, go in there, get all the details, longitude, latitude, which elevation it has. Other important information is that you have a traffic control that is responsible for that, where it's located. Here's a phone number. So if you try this phone number, calling 530-389-2091, you get a voice message, a robotic voice telling you what's the weather conditions in Blue Canyon right this moment. And this phone number is constantly on and run by FAA. Here on the right-hand side, you have the sectional chart I was playing earlier. So if you click on that particular for Blue Canyon, it's going to take you here, right? In the center is going to show you Blue Canyon. What you do is you put your cursor on the little blue thing here. Let me see if I can zoom. Yep, I can zoom. I think that was the maximum zooming. If you click this little blue square, it's going to present you with data. And that's the data I was presenting on the slide earlier on. And here's what kind of weather services are provided. The TAF. TAF is the most detailed weather reporting for aviation. That's also very necessary for us astronomers too. Now, you can also click a button here called Nearby Meter and TAFs. And what that's going to tell you is based on how many miles from Blue Canyon away there are other weather stations, and everything is nautical miles. And you can actually click on those and go there and get practically the message for the weather here. And up here you have small links. WX stands for weather. And when you click it, the first message is the weather. And because this is a TAF message, TAF, can control copy. And I also provide a link on how to translate that. You can go to a TAF decoder here, paste it in, and here you get the message decoded. It tells you wind direction, tells you the speed in 9 knots. Visibility is infinite. There's no visibility obscurity here. The sky is clear. Remember those code I was showing that diagram earlier on in the slide, SKC, sky is clear, and so forth, all kinds of data here. Now the cool part here, let's see if I can find the, sorry, my mouse a little bit. Any questions this far while I'm looking for the meter message?
No questions. Kevin is pointing out that the SAVAS website, svas.org, has images of the sun from NASA that seem to be updated more frequently than space weather.
That's great. Thank you, Kevin. Thank you for sharing that information. Okay, let's see. There. I'll find you soon. Let me see, in case I have it in my bookmarks. Probably it's something I missed out, and my apologies for that. But there is a website that provides you meter reports, and the cool part about that, about our Blue Canyon, is that I can extract the snow depth and all that stuff. And for curiosity purposes, let me show you particular, if I have it still. We'll collect some data over time from the Blue Canyon weather system, and I paste it inside my Excel, and I can see here the dew point and temperature curves, temperature in blue and dew point in red, that you can see direct correlation, like I was explaining earlier in the slide, that temperature goes up, dew point is going up as well. And here's the relative humidity, and if you compare the curves, they all look almost identical based on this data from our weather system located right next to the observatory. And this is the column that's interesting, the snow depth medium. And I'll give that information to Kevin and Raj so they can distribute to you guys, and you can look what does medium snow depth means. But this is data collected in February, and I did that intentionally just to show you guys that we have snow data here, and sky condition data as well, where it tells you that the clouds and different layers. So we divide in different layers. Remember, guys, I was telling you about the 3 different layers: the high altitude, the medium, and the lower. Those are the sky condition layers that we were talking about. And all that will be provided to you, so you can investigate yourselves and play around with those facts and numbers. The interesting part here is that local weather data is this instrumentation that's provided to us is kind of golden. That's also because it's right next to our very own observatory, next to our tarmac, is that we have very accurate weather data that we can use for observation logs, for planning our observations, for determining how, instead of asking Stuart, hey, how is the snow up there? You have it right here. All that stuff is determined by those equipment that we can, find out exactly what the conditions in our observatory are at any point of time. Now, these reports are being provided every half hour. So every 30 minutes, we get constantly an entry from FAA into this database. And I'll organize my links in an orderly manner. So when Kevin and Raj distribute those to you, you can click around and see where you can gather that data from. But you can play around with it and see here. This is fascinating. Any questions? Finally, I want to show you live here how we work as developers in those systems is that, of course, we can't have a bunch of sensors connected to our PC, to simulate so we have a simulator here that determines runway A, runway B, we have transmissometers that bombard data into our system, and ground temperature sensors, whatever else the airport is. And for each airport, we have a special configuration file that we load up into the system and starts measuring, pretending it's the sensors, and then they fall into our system that we developers work on. And here we have the MET report I was telling you about. I can actually go to take one of the meter reports, just copy it for fun and just see what the simulator produced for us, and go to this website I was trying to show you earlier. And go not to the TAF, but to the meter here and see what, okay, it's a meteorological aerodrome airport, stands the meter for. So the airport identifier, it tells us every timestamp is UTC, they use universal time zone or Zulu time, so called, and wind direction, speed, visibility, and so forth. Light rain, if it's raining, and so forth. So this is how you can decode those messages. Over time, you might avoid the decoder because you're going to recognize those symbols and numbers. But if you don't want to, of course, here are the decoders where you just copy paste the message. One more thing is when you call that phone number I was showing on the website before for Blue Canyon, it actually the voice is telling you in clear language what the weather conditions are. You don't have to interpret Zulu or knots or anything like that. Weird, it's going to tell you the conditions.
Okay, we do have a question from the audience from Martin Bailey. In your opinion, have you used the ICSC Clear Sky Chart Viewer from the Apple App Store?
I have not.
Okay.
Martin, could you please tell us more a little bit about that? I can learn something from you as well.
Well, I picked it up at the App Store. It's produced by a group called Random Widgets, and it provides more of a probably the same information, but it's color coded and pretty granular. So it looks at cloud cover, transparency, seeing smoke, wind, humidity, and temperature. And
what was it called again?
it's called, okay, let me get back to it again. It's called the ICSC. Hold on.
Clear Sky Chart Viewer.
Yes, the ICSC Clear Sky Chart Viewer. Thank you, Raj.
And
That's
it's
from,
an app,
that's from the
right?
message you put in chat. So
Yeah, right.
it's an Apple app, iOS.
Interesting. I will look into that and find out where it gets its data from, and tell you how it's parsing it. It's probably gathering the data from those
Well,
ASOS. Go ahead.
yeah, it's specific, has a specific listing for Blue Canyon. So
Nice.
yeah.
Really nice. I know the something I didn't show you guys. Sorry for my apologies for jumping on my website because I don't have the URL in my head right now. Bottom, I have a little widget. This thing. It's actually very, very useful for. Yeah, most of you must have seen it, but I'll share this link as well. It's excellent source of information where you can actually pinpoint your location and hopefully has entries for the sky conditions at that
As
point.
Attila Danko's website.
So we've got that on our website also, a link to Blue Canyon's Clear Dark Sky view of that.
And another cool thing is they have light pollution here. Let's see. Oops, this is a not new big mistake. Let's go back again. I like this. I don't have the coordinates in my head, but you can actually add the coordinates, and actually, I think this is Sacramento centered here, right in the crosshairs. Yeah, it's No, it's dependent because I clicked from that map over. So yeah, it still is the Sacramento area. But it's telling us how much light pollution it is with a scale indicator down here, a chart. Perfect. Yeah, it's a really awesome website, and I think I have it also on the links on the slide. Yeah, I'll definitely look at the app and see and gather more information where it comes from. So absolutely. Thank you. Any other questions? Did you guys find this information useful? Did you know that the ASO systems rig right next to us can be that useful? Did you guys knew that the information can be accessible to anybody at any point of time?
Well,
I had a vague idea, but I didn't know the details. So this was extremely useful and very illuminating.
Cool. Yep.
Sorry, Kevin, that you had a comment.
Well, no, it's just way cool. I didn't know. I'm kind of.
Do you have a list of those websites that I could screen prep?
Yes, sir. I'll compile them all in a list, and I'll let Kevin and Raj distribute them to you. I'll send.
Oh, okay, great.
Yeah.
And, yeah, this is information. You know, this is where our tax money goes, so you better start using it.
Yeah. Do you know if there's an API for accessing the Blue Canyon weather site?
Absolutely, there is.
That's neat.
Yes.
Right.
So yeah, it's coming back in textual form. You can get back as JSON format, whatever you like. As a developer, you can integrate that to your system. Yeah, FAA has done a wonderful job in distributing those ASO systems across our country. They're uniformly distributed. So, you know, especially these days when we have weather that gets more radical, more violent, it's essential. You know, meteorologists using this data as well. It's not just for aviation; it's for actually anybody who cares about weather. And why not as astronomers going in there and start using that too? I know in Morocco, for instance, where we launched one of our systems, they use it for agricultural purposes too. So yeah, it's being used widely and broadly into different areas.
All right, any other questions?
Thank you for having me tonight. It was
All right.
a pleasure, and it's great to see you, all of you again, and see that you're doing well. And I hope to see you around soon and have the chance to
Absolutely,
observe.
Niklas.
Thank you so much.
Thank you very much, Niklas. This was very, very enlightening. Shed light on something that I only had the vaguest idea even existed.
Yeah.
I knew obviously that these towers had a purpose, but you're breaking down the data and providing a literal translation for us. Just remarkable.
Yeah, this is great. Very good.